Our next speaker likes to, in her free time, she trains acrobatics. So I want to know, is she being trained in acrobatics or is she training other acrobats? Everyone, please welcome Jordan.
Thank you so much, Jared. To answer your question, prior to a knee injury that I am currently dealing with, it was both. Now it's nothing. But back to the subject. So I will be sharing with you guys today a model that we built to classify medical conditions using natural language processing. Natural language processing, abbreviated NLP, is basically when we use AI to understand human language instead of ones and zeros, right? So English, Spanish, Mandarin, it doesn't matter. This type of AI is really good on unstructured data like text or audio. And the techniques that can be used to accomplish this type of analysis range from, rules-based entity extraction, entity recognition, to statistical modeling, to machine learning and deep learning. So in particular, when it comes to medical data, NLP has a really important role for a number of reasons. So first of all, if you're more than a few years old, probably some of your medical records were originated on paper. And we need to be able to pull the text off that paper and understand it if we're going to be able to analyze it. Even in terms of recent records, sometimes some hospitals or healthcare providers are working with legacy systems. Maybe they print out a form and you have to fill it out by hand because they don't have enough computers. And then even if we have the most up-to-date, perfect technology, when we talk about, the clinical progression of an illness or sort of abstract symptoms that we're feeling that we don't have a diagnosis yet, we're going to need to use descriptive language and kind of descriptive summaries. So NLP has a really important role in analyzing medical data. But when we talk about medical language, so of course, especially if I'm a patient describing my own symptoms, probably I'll use really simple words like my ankle hurts or my ankle is swollen. But a doctor prescribing a diagnosis or, a patient repeating a diagnosis that they have received is going to involve, words like osteoarthritis or these more technical, specific medical terminology, which come from Greek and Latin roots. They have prefixes and suffixes. And honestly, the syntax around the way we put those roots together is a little different than the way it would be in English. So any NLP modeling that we use to handle medical language is going to need to be able to accommodate both regular simple English and these more technical Greek and Latin-based medical terms. So if we look at the client case that we built this model for, there actually were many steps, but we're going to focus on these three. So we needed to work with records as far back as the 1950s. So some of them were definitely paper. We needed to be able to scan records off of paper, extract the data and save it as text. To do that, we used OCR, or optical character recognition. You've probably seen these 8s before. It's just machine learning that specializes in recognizing characters like numbers, letters, punctuation in two-dimensional images and saving them as the corresponding ones and zeros for the computer to understand what character they are. Once we have this text saved, our classification task, which is what I'll focus on, was to sort the conditions into medically relevant categories for processing downstream in their system. So therein lies the first challenge, which is that we had over 100 medical categories that we needed to be able to sort cases into. We know that your joints are orthopedic injuries or conditions, but each joint has its own specialist. So you have a wrist specialist, an elbow specialist, a shoulder specialist, etc. And then you get into the internal medicine, like the body systems. You probably remember those from 8th grade biology. You have your digestive system, your respiratory system, your endocrine system, and extra points if you know what the endocrine system does. So we had a lot of different categories that we needed to be able to sort these strings of text into. A couple other challenges we were facing is that we actually did receive training data from the client, which was great. That doesn't always happen. But some of the data that we received had contradictory labeling. So for example, a single condition would be labeled as 2 different categories throughout the training set. And there were also some categories that we needed to be able to classify conditions into that we didn't have any examples of in the training set. So the training data was obviously better than nothing, but it wasn't ideal. We still had some problems there. And then because of the nature of some of the scans that we were working with, the OCR was producing some errors with, poor scans or perhaps great scans, but poor handwriting. And you can see some examples here. So actually, to address that, the first thing we did is make sure that we had a spell check layer that we could feed the text through before we even got to any classification to correct for those small OCR errors. So for some examples, we can see, so diabetes affects the endocrine system. Now you know. Carpal tunnel is a wrist condition, so that goes to orthopedics, wrist. Pancreatic cancer is cancer, so it's going to be oncology, but the pancreas is part of the digestive system, so it's oncology, digestive system. On the other side, we have pancreatitis. Your pancreas is still your digestive system, but it has nothing to do with cancer. So you can see how we have some really thin lines between the categories. And then, so bullet wound in left hip, there's a category for like wounds and trauma. Super fun category. So the original model that we tried out, we had the input text, we put it through the spell check layer, like I mentioned. Then we extracted some features. We extracted keywords, specific, names of illnesses, organs, body parts. And then we also extracted trigrams. So in this case, trigrams is referring to groups of 3 characters. So for the word trigrams, it would be TRI, RIG, IGR. And that helped us a lot with the prefixes, suffixes, Greek and Latin roots, and the fact that a lot of the technical medical terms were very commonly misspelled, which I really can't blame anyone for because I can't spell any of those words either. Once we had these features extracted, we threw them into a multi-layer perceptron, which is a simple neural network, and it spat out a classification for us. So this worked okay. We had a really wide range in accuracy from retrain to retrain. Even though we had over 20,000 training cases, rows of training data, we also had over 100 categories. So if you think about it, it's really not that many examples per category. And the distribution of cases across category was really varied based on just what had come in the medical system that they were pulling the data from. So it was a pretty unstable model, and it really struggled with cases that crossed categories. So bullet wound in shoulder, if you think about it statistically, both in the training set and it was reflective of, so it's a US-based client. So in the US, there are many more orthopedic shoulder injuries than bullet wounds and trauma wounds in shoulders. So, statistically speaking, the model has learned that if the word shoulder is mentioned, it's more likely that it'll be an orthopedics shoulder classification than a bullet wound classification. And playing around with that in terms of weighting the data set was causing a lot of issues with overcorrection, and it really didn't seem to be the solution. So, we were looking at this and trying to figure out how we could improve this underperforming model. And I think a lot of times in our field, the instinct is to kind of pull out the big guns, be like, what deep learning can I throw at this? What super fancy model can solve my problems with magic, But the main advantage that deep learning brings in NLP is that it allows words to be understood in their greater context, right? If you have like a paragraph of text or even a sentence. But in this case, we are looking at very short strings of text, maybe 3 or 4 words, excluding stop words. And even, people will write just a list of words or kind of shorthand. So there wasn't a lot to be gained from contextualizing the words that we were looking at. So deep learning really wasn't the solution. And I mentioned earlier, we basically were swinging the model from side to side. Like we would get some success in some parts with one model, some success in other parts of the classifications that we needed with another model. And so we really couldn't, neither of the things that we were trying were really solving our problem. And so what we ended up doing was using both. And so we had the best of both worlds. So we moved to an ensemble model, which was hybrid. It used both rules-based classification and machine learning classification. So I'll take you through it. We had the input text. We ran it through the spell check, just like before. And then we ran the text through a set of rules. And these rules covered a lot of the cases where, for example, with trauma, we needed the model to focus on particular terms, weight particular terms more than others, and just weighting the simple training set was not was causing errors in the opposite direction. It was overcorrecting. So, for example, for the bullet wound, we had a dictionary of terms that describe violent traumatic injuries. It was a really pleasant dictionary to compile. And if any of those gruesome words is found in the text that we're trying to classify, then the rule about wounds and trauma catches that text and sends it straight to classification as wound/trauma. It doesn't, it just bypasses the machine learning models completely. So the last rule that we send it through, if none of the other rules caught that text, is to determine if there's any indication that the text we're looking at involves cancer in any way, because the client had emphasized that even if multiple conditions were present, if cancer was one of them, cancer will have a lot of like secondary conditions that come from it, but the cancer is the root. So they wanted cancer to be prioritized. And so we made a cancer model if that the text would be sent to if it had any indication that cancer was present, and a non-cancer model for all the others, and those are mutually exclusive universes of classification, I guess. So these machine learning models work basically the same way as the original model does. They're just streamlined in their classification tasks. So each of these submodels has a smaller set. We have 3 submodels. And each submodel has a smaller set of classification tasks, which allows them to really focus on, I know I'm speaking about the models like they're people, but we kind of feel like they are. So it allows them to focus on their more narrow classification task, and the results are less diluted by the sheer number of categories that they're trying to sort things into. So back to these examples, if we see it in practice, for the first 2, it didn't really change much. We had diabetes and carpal tunnel. They aren't picked up by any of the rules, and neither of them have anything to do with cancer. So they're just classified by the non-cancer model. Pancreatic cancer, of course, cancer is an indication that cancer is involved. So it gets sent to the oncology model, which now has a much easier task of just, it only has oncology classifications to output. So I think there were 13 different oncology-based classifications, and they, once we know that it's cancer, it's really easy for the model to understand that the pancreatic means digestive system, and so it doesn't dilute the probability of that specific classification by having the other digestive system category there watering down that probability. So on the other side of the same coin, we have pancreatitis is in the non-cancer model, and that non-cancer model can classify it as digestive system in a really confident way, with a really high confidence, without having that confidence watered down by the presence of another digestive system classification. And finally, our favorite bullet wound classification. Bullet wound is obviously in that gruesome dictionary of wounds and trauma terms. And so that was caught by the rules-based classification and sent directly to that classification without needing to involve the machine learning models. So this solution resulted in a much more stable model. It was much more accurate and much more consistently. And it really fell in line with exactly what the client wanted. When they wanted certain things to be weighted, we were able to accommodate that without sacrificing sort of accuracy in other places. So it also allowed us to overcome the gaps that we were facing in the training data. Instead of having to follow up with the client that we really need this data, we can't finish the model until we have it. We were able to say, we were able to just devise a set of rules by having a simple conversation with a subject matter expert. So that was a lot less burden on the client. It worked for us. Everybody went home happy. And then this solution also allowed us to have that clear distinction between these kind of tricky cases to know exactly where we needed to weight those particular terms that were more important than the others. And finally, it wasn't strictly part of the ensemble model, but we did, while we were adding rules into the mix, we did add some new tricks. Like we added a rules-based flag to identify particularly severe disease for prioritization in the system. So basically, the moral of the story is you can have it all. You can't, if two models are working, one on one half of what you need and the other on the other half of what you need, hybrid models and ensemble models are going to be a really great way to combine them and kind of get the best of both worlds for optimal results. And that is the end of my presentation. Thank you guys so much.